IPv6 brings very interesting option. This is not static, and it is not DHCP, which for someone with an IPv4 background, that would be inconceivable. What if I don't have static and I don't have DHCP? Well, I got nothing. So another option that IPv6 brings is called SLAAC, SLAAC, Stateless Address Auto Configuration, SLAAC. It's plug and play. It happens automatically. What happens is the router or a layer 3 device must be configured to provide the network, the prefix, the subnet prefix, or the first 64 bits. In IPv6, out of the 128 bits, the first 64 are always the network and the last 64 are always the host. So there is no subnetting. There are subnets, but there is no subnetting. There is no boundary that we move, or bits that are host and bits that are networked. It's just 64 bits network, 64 bits host. And the router can then be solicited. The device comes into the network and says, hey, is there a router out there? Can any router hear me? And then sends a router solicitation. It says, okay, what's my network? And the router will then send a router advertisement saying, hey, look, this is your network. So the device now knows the network, and the host is configured automatically by using its own MAC. The MAC is hexadecimal. It's globally unique. At least the MAC address is supposed to be globally unique. A little on that following. It uses a process called EUI 64, Extended Universal Identifier, 64 bits, and basically takes the MAC, splits it in half to maintain the integrity of both values. So there's the OUI, the first part of the MAC, the first 24, what we call the high bits, the high 24 bits, the first 24 bits of the MAC are the OUI, the organizational unique identifier, or the vendor, the manufacturer. And then the low 24 bits, or the following 24, the last 24 bits, are the actual serial of the card. So we maintain the integrity of both elements. And well, we're falling short because the MAC is 48 bits and we need 64. So we introduce a sequence of bits FFFE, which is a delimiter. A delimiter is a number of bits and with value of 1, followed by a 0. Just like if you see a preamble on an Ethernet frame, it's just a bunch of ones to the left with a start of frame Z. The 0 tells the card, okay, the frame starts here. So what happens when devices are reading these bits, they start reading the OUI, they get to the 25th bit, and you see a bunch of ones. F is 4 ones in binary, so 4 more for the F, and 3 more for the, so out of the 16 bits, 15 are 1, and a 0 at the end. The next field starts here, so then the devices know that, just separate, delimiter. And also because of the way that the OUIs were assigned some overlapping, the 7th bit, it's called a UL, is a universal UL bit, that is flipped, and that's just to guarantee a globally unique address. IPv6 then, based on the MAC, it has to guarantee global uniqueness. So look at the UL bit and how it's flipped, just to make sure that that sequence of bit is unique globally. And this happens outside of static, outside of DHCP. IPv6 devices can have more than one IP. Just letting you know, more than one static, more than one DHCP, could have more than even unicast. They could be members of multicast groups, Anycast, which is a new addressing. I really welcome you in looking into IPv6. It's really interesting, where devices are no longer limited to just having one IP. Very, very interesting. So SLAAC, stateless address auto configuration, can be used in addition to static and DHCP, or instead. So the process, the device shows up into the network and it generates a link local, what we call an FE80. It's an automatically generated. It's one of the IPs that the device can have. There's FE80 or link local. If you see any IPv6 device, it will have an IP that starts with FE80 and it is strictly local only. It will never get global access, will never get public internet access. The host also joins the all host multicast group. For IPv4, that's 224.0.0.1. It means, hey, I'm a computer, I'm a host. The routers are members of the 224.0.0.2. And IPv6, that would be FF02:1 for all computers, and FF02:2 for all computers. So you're calling, hey, all computers out there, what's my network? Is there any gateway out there? So you have more than one router, then you have gateway redundancy embedded in the protocol. Both routers will reply with a network, and you could have them a device with gateway redundancy, first hop redundancy, or they could be multi-homed, because this device could get different networks from two routers, so immediately it belongs to two different networks. See how flexible. It's really, really empowering the options from IPv6. And then at this point, the device is going to send a router solicitation. Hey, is there a router out there? The router will reply with the prefix 2001 DV8 CAFE. What a original network that I would love that network. Okay, one, and those are the 64 bits for the network. When the device, the computer, receives that, then generates its own host part with its own MAC. Or we could have an option to randomize just for security purposes. You might have wondered, hey, if I put that as my host, then somebody will be able to know what is my MAC. That is true. But the EUI64 is honest on the local network. Once it goes global, it's always randomized by default. That's just a layer of protection. So don't worry about that too much. There is a duplicate address detection, DAD. That just to make sure that every device has its own unique address, and there are no duplicates. So you see how devices can just come into the network, get the network address from the first 64 bits from the router, build their own EUI64, and we have basic connectivity, basic reachability. From there, we would bring the sophistication of DNS, DHCP, and then build the network. This is just to have basic connectivity out of the box, not be too concerned. On DHCP version 6, we also have that possibility. even dynamic DNS, very flexible, very efficient. It's the same, operates very similar to IPv4. Certain things you have to consider. You have two ways of doing it. You may have a four-way negotiation, which is the way that you know it, just with different names, or you have a two-way version. What's a rapid commit, RC, something like RC DHCP, rapid commit. You need an IP, here's your IP. Next. It's just very efficient. There's no back and forth negotiation of, hey, I need an IP to discover your solicit packet. Then there's the advertise, or it's called offer with IPv4. Hey, here are the available ones. Choose one. Let me see if it's still available. I'll grant it to you for this long. In this case, in the rapid commit, doesn't happen. With the rapid commit, it's just need an IP, take your IP. Next. There's no, if you use the four-way negotiation, some find it more secure, some find it that with the advertise, we can shape things, we can have more detailed configuration. But it's just really, if the purpose is to get an IP, rapid commit, more efficient, much faster. DHCP also offers DHCP Relay, and it is the same interface that is expecting the broadcast. In this case, is not really a broadcast because IPv6 doesn't use broadcast anymore. But the DHCP message, when it is received by the Ethernet, then you will place the IPv6 and DHCP relay destination command. Just IP helper with IPv4. You just have to type a little more. I guess typing more with IPv6, right? How can that be? IPv6 DHCP relay destination and the IP of the DHCP server.